All right, we are going. Okay, so here's where we're picking up from last time. We're going to ask a couple of what I'm going to call natural questions to ask. If you're interested in a given function, you want to know how it's changing, how fast is it changing, that kind of thing. A couple of very natural, reasonable questions. Here's the first one. So you see we've got a function here, and I've drawn here the what I like to call the literal picture, right? So you can see the domain, you can see the target. And the question what I ask is, supposing that I am at some point A, and supposing that I am entertaining all possible directions from A that I could start moving. Right? Now, of course, for any given direction that I start moving, the function's going to be changing, and in particular, there will be an associated directional derivative representing how fast the values of the function are changing. So the question is, which one of these many different directions from A that I could start moving, which one maximizes this directional derivative? Which one of these green directions makes my resulting directional derivative as big as possible? Right? A reasonable question to want to ask. You can imagine many scenarios where, maybe this is where I'm standing and I'm cold and I want to start moving in whichever direction is going to make the temperature go raise as quickly as possible. Right? Because I don't want to be cold anymore. Now, of course, whatever direction I'm going, obviously, the faster I go, the faster the temperature will change, of course. Right? So run, don't walk. Yeah, absolutely, of course. But I want to isolate the question of just which direction. And so specifically then, we're going to restrict our question just to unit vectors representing directions, and then once I find the right unit vector, then of course I'll run as fast as I can in that direction. Okay. All right, does everybody see the question? So now I want to talk about how would we describe the answer to this question before we actually answer it. And let's talk again about what it is that we're trying to maximize. We're trying to maximize this directional derivative, and among other interpretations we have for the directional derivative, it's how fast is the function changing per unit distance. So if you think about it then, if we're trying to find which direction should I go that makes how fast the function is increasing as big as possible, wouldn't it be reasonable to call this the direction of fastest increase? Because that's the direction you go to make the function increase as fast as possible. Right? I think it's very natural language. It practically justifies itself. Right? Okay. Now here's a different point of view you can take. Also reasonable. Also common, by the way. The directional derivative tells me the slope of the graph. Now, true, it is the slope of the graph. I'm going to point out there's an asterisk on this. You'll notice there is no graph in the picture we were looking at. In fact, there isn't always a graph. Depending on the dimensions involved, there might not be possible to draw a graph. But if you were looking at a graph, then you could interpret this directional derivative as being a slope. And so this direction, the answer that we're looking for, whatever direction that is, if that's the direction that makes the slope as high as possible, wouldn't it be reasonable to call the direction that we're looking for here the direction of steepest ascent? So in which direction should I go so that the graph is increasing as steeply as possible? All right. So two different terms that you could describe the answer to this question with. I will point out, by the way, that of these two candidates, the one that is most common, at least in my experience, is this one right here, direction of steepest ascent. You're going to hear that most of the time. I think that's unfortunate. After all, this only makes sense if you're looking at a graph, which we might not be. graphs are hard to draw for multivariable functions. Best case scenario, they're three-dimensional pictures. Best case, right? So my own personal preference, and what you're going to hear me say mostly throughout this course, is direction of fastest increase. Because that makes sense no matter what the context, no matter what the dimension, no matter what kind of a picture you're looking at. It just naturally makes sense. So I like this term better, but I'm in the minority on this one. Okay, is everybody with me on what the question is asking? All right. Okay, so let's answer the question. How are we going to find it? Okay, well, this is what we want to maximize, directional derivative, which is computed by that formula. It's a dot product. How do we compute dot product? Well, I guess we have different formulas, but here's one of them. So here is yet another point of view on what it is we're trying to compute. We're trying to maximize. We're trying to make this expression as big as possible. Don't forget, though, we're only interested in unit vectors, and that means that this factor right here, the magnitude of v, if v is required to be a unit vector, its magnitude is 1. So really, actually, when you get right down to it, this is what we're trying to maximize. This is what we're trying to make as big as possible. Magnitude of the gradient times the cosine of the angle. And let's just kind of think about that for a minute now. Keep in mind, we are at some point A, and I haven't started moving yet. We're just kind of contemplating the different directions in which I might eventually start moving. But for all of these directions, I'm at the same point A. And so that being the case, this factor here is a constant, because the gradient is just a vector at the point A. It has a magnitude, and it's the same A, same gradient, same magnitude for all of these different directions, because they're all at the same point A. Okay, so really then, altogether, what we're actually trying to make as big as possible, the actual challenge here, is just cosine theta. We just want to make cosine theta as big as possible. Oh yeah, question.
Sorry, can you explain one more time why the v goes away? Is it because it's a unit vector?
Yeah, because it's a unit vector and its magnitude's 1.
Yeah.
Yeah. So how do we make cosine theta as big as possible? No problem. Cosine theta is as big as possible when theta, namely this angle between the two things I'm dotting, when that angle is 0. So easy, right? So the answer to our question then, the unit vector we're looking for, keep in mind we're looking for a unit vector like that. We're interested in the expression, which is the dot product with the gradient. We've decided that this angle here, theta, should be 0. And if that angle theta is 0, then I need to redraw my picture. The way I make that angle 0 is to have my vector, my direction of fastest increase, point in the exact same direction as the gradient. Everybody with me? All right. Cool. All right. Now, so we have an answer to that question. Now here's the next perfectly reasonable question. Okay, cool. We know what the direction of fastest increase is. Which direction should I run if I want to get warm as fast as possible? Pretty natural thing to want to know. How fast am I going to be getting warmer as I move in that direction, right? How fast? What is the rate of change of temperature with respect to distance traveled? However fast I should happen to be running in that direction. And don't forget, rate of change with respect to distance traveled is the directional derivative. So I want to compute the directional derivative, this maximal directional derivative, in the previously decided upon direction, the direction of fastest increase. And so again, we compute directional derivatives with dot products. Again, we've just decided that v is the direction of the gradient. Then I can look at gradient dot gradient, that is magnitude squared, And then I find myself with magnitude squared divided by magnitude, and of course that just gives me magnitude. So what we have then is another natural question with a kind of a crisp answer, namely dfds in the optimal direction is the magnitude of the gradient vector. Nice and crisp and simple. So this gives me what I need to make this what I call purely geometric characterization of the gradient vector. And before I go into it, I want to point out this is a little bit of a surprise at this point. Reminder, where did the gradient come from? What have we heretofore done with the gradient vector? Well, it was a notational convenience. It allowed us to not have to go ... and have a bunch of terms there that all look kind of just alike, right? It's just notation up to now. Purely algebraic object. And now what we have is that the gradient is the unique vector that has these two geometric features. It's a vector whose direction and magnitude are answers to simple questions. It's the vector whose direction is the direction of fastest increase. Its magnitude is dfds in that direction. All of that being geometric, direction and magnitude. So it's a wonderful sort of change, kind of shift in perspective then on gradients. Gradients don't have to be viewed as purely algebraic things. They can be viewed as geometric things. They mean something geometrically. So everybody okay with that? Nice conclusion. Okay, example. I'm going to start off with a little bit of a discussion of language. First, let me state the question. We have a hill that's in the shape of a graph of a function. Y'all remember how graphs work, of course. You have a function of two variables. The graph says z equals the value of the function, and then that gives you a surface. Okay. All right. So we're going to be talking about various places, various locations that on the graph. And here's the point of language I want to get to. This is me right here. Right? I'm on the hill. And yet, when we describe my location, and let's just think about the real world for a second here. When you describe your location, longitude and latitude, nobody bothers to say longitude, latitude, and altitude above sea level, right? Because why would you? Of course, I'm at whatever point is on the surface, whatever, right? I mean, if somebody says, yeah, I'm at latitude, longitude of Duke campus, and by the way, I am also 300 feet elevation above sea level, because of course you are. Where else would you be? 300 feet below the ground? No, that's silly. Right? There's no reason to distinguish between the longitude and latitude that you might view as being just x and y coordinates versus where you physically are in 3 space, because we live in 3 space, because it's obvious. Your z is just the value of the function. So heads up about this. In this question and others, these 2 points are going to be conflated. I'm going to talk about these points sort of interchangeably. Here's me. I'm at the point 1, 3. Right? And etc. So anyway, be heads up. Be aware of that little issue. All right. So with that in mind, if I can get this erased, there we go. Oh, there we go. Okay, with that in mind, the question is asking us which direction is uphill and how steep is it at that point. Now let's rephrase the question before we get into it. Which way is uphill could be rephrased as which way on this graph would have me climbing up the hill the fastest, which could be rephrased as which direction at this point is it the steepest which could be rephrased as, what's the direction of steepest ascent? This first part of the question is, other than semantics, directly asking what is the direction of fastest increase, what is the direction of steepest ascent. Is that cool? All right. Second question, how steep is it there? How steep is the mountainside? Well, how steep is the mountainside is another way of saying how much altitude do I gain per unit distance that I move in whatever direction I'm going. In other words, it's rate of change of the function with respect to distance. In other words, it's the directional derivative in the optimal direction. So, again, language aside, these two questions are just asking what are the direction and magnitude of the gradient vector. Is everybody with me? Yeah.
Do you know it's southwest because of the signs?
Yeah. Well, you're getting ahead of me here. Yeah. We'll get to that in a minute. Yeah. Okay. Is everybody on board with the idea that really all the question is asking is direction of the gradient and magnitude of the gradient? And at that point, it's kind of all algebra here. So we've got our function. You can take the gradient. You plug in the point in question. We're looking at the point 1, 3, which we plug in, which makes our gradient turn into this, which is like so. And now what direction is that? And when you draw a map, most of the time, not that you have to, all exceptions granted, but most maps, north is up, right? And if north is up, and we tend to draw the y-axis up, north typically is just in the direction of the y-axis. And if north is that way, then the direction of that vector is southwest. Did that answer your question? I'm not sure if that... Okay, yeah, cool. Yeah. So, southwest. And how steep is it in that direction? Well, it's pretty steep. The magnitude of the gradient tells me how steep it is, and 2 root 2 is nearly 3. That's like, what's that, 2.8 something? That'd be a slope about like this. That's really steep. That's definitely use your hands climbing, right? This is not a casual walk. Okay. Everybody okay? Alrighty. Moving along, let's talk about level sets. Recall, you have to be actively, consciously attentive to what kind of a picture are you looking at. Very importantly, here we were looking at a graph of a function of 2 variables. Here, now, still a surface. This is no longer a graph. Here we are looking at what is given as a level set. Right? Level set, where some function is equal to a constant, and notice that this being in 3 dimensions, this is a function of 3 variables, as I have it drawn here. Right, it's a different kind of function, a different kind of picture, not a graph as written. Okay, now, I'm going to make an observation about what happens when you're at, let's say, a point like this. And I'll tell you what, I'm going to go ahead and see if I can zoom in. Oh, I want this. It always takes us a minute to catch. I don't know why. Here we go. Here we go. Okay, so at a point like that on the level set, keep in mind, being on the level set, the value of the function is c, whatever that constant is for that level set. Imagine that I were moving along a path like that, all of which is on this same surface, same level set. Well, that means that the value of f, this function whose level set I'm looking at, the value of f here is c, and here is c, and here is c, and the value of f is just c everywhere along this curve because the whole curve is on this level set where f equals c. So on this curve, f is constant for the entire curve. And now let me ask a related question. Okay, so fine, the value of f is constant. So now I'm going to ask, okay, well then as I move in that direction, as I move along this curve where f is constant, as I move in that direction, how fast is the function changing? And I propose that if the function's constant, then the rate of change is 0. Everybody buy it? Did I see a hand somewhere? Yeah, go ahead. Yeah.
Why is it a curve if the level set is like a cross-section graph?
Well, there's no graph in this picture. Yeah, now if there were a graph, then you could make some argument about how this is a cross-section of it, but that's a tough argument in this case because the graph would be some sort of a hypersurface in 4 dimensions, and how I would visualize that is what it would mean to take a cross-section of that. That's a brain melter, right? So I would say don't think of it that way. There's no need to think of it that way. We have no interest in the graph of f at this point. What we're interested in is that this surface is where this function of 3 variables is constant. That's really all we need to know about f. Does that make sense?
So f is in terms of x, y, and z.
Correct. F is a function of 3 variables because this equation has 3 variables because it lives in a 3-dimensional. Yeah, 3-dimensional. Yeah.
So in this case, the tangent plane is just like a surface that follows the same contour as the function.
Yeah. Mm-hmm. Yep. That's right. It's literally as you would hope. It's tangent to the surface. Yep. Yep. All right. So, in this situation, let's see here. Let's do it like Okay, there we go. So as we are at that point on that purple curve, moving along the curve in that green direction, the rate of change with respect to distance is 0, but now remember, rate of change with respect to distance is what directional derivative is, and that means, and furthermore, directional derivative is computed with a dot product, so if that's 0, then that dot product is 0. And we hopefully all just had a reflexive knee-jerk reaction because we heard someone say the phrase dot product is 0. When a dot product is 0, the vectors are orthogonal, right? So that's the beautiful punchline here is that gradient vectors are always orthogonal to all tangent vectors. And now I make a geometric appeal. If this gradient vector has to be orthogonal to all of the tangent vectors, there's really only one way that's possible, and that is if the gradient vector is perpendicular to the surface itself. And that's the big punchline. Let's see here. Gradients are always orthogonal. I should say perpendicular at this point. Always perpendicular to level sets. Gradients always perpendicular to level sets. Everybody happy? Mm-hmm.
How can the gradient be perpendicular to the entire curve and it's not flat?
Well, it's just at that one point. Yeah, no, you're right that I'm not claiming that this one vector is perpendicular everywhere. It's clearly not perpendicular over there, right? But at the same point where you compute it, in other words, if I compute the gradient at that point A, then they are perpendicular. The gradient is perpendicular to the surface at that point A. Is that satisfying?
Yeah.
Okay, yeah. So then over here, if I were to look at some point over here, the gradient's actually going to be a totally different vector, and at that point, that gradient vector is perpendicular to the surface. Yeah. Okay. All right, really nice fact. This is one of the most important components, elements of what I would like to call the calculus of level sets. Now, y'all heard me say this phrase a million times way back when I was pitching this claim that I was making. That got to be really clear in your mind about the difference between graphs and level sets, and you got to treat it like a level set if it's a level set. You got to treat it like a graph if it's a graph, and make sure to know the difference. So what I described as calculus of level sets was geometric facts relating calculus objects to level sets. That's what this is. Gradient is an object of calculus. And here I have a geometric statement, perpendicularity, about how that object of calculus relates to level sets. So calculus of level sets. And very importantly, requires that you're looking at a level set. All right. This next page and a half, I'm going to go through pretty quickly. I think it's highly readable, and again, tough choices and all that. Of course, we're a little behind schedule, but this is very readable, I think. It's just an example of how to use the idea that we just talked about. And I'm going to hit the highlights, but I'm going to suggest that y'all go through the details to make sure that you see all the, therein lies the devil and all that. So make sure you're good with all these details. I want to ask a question that we already know the answer to. How do I find the equation of a tangent plane? It's old news. It's the graph of the linear approximation. Right? We have that answer. I'm going to show you a different way to think about it, a different way to derive it, and this tool has uses in other ways. Okay, so here we go. So we're going to start off looking at a surface S that is a graph. Keep in mind, that's what a graph is. And a graph is when you set a function equal to a new variable z, such as in this case. And that gives you a surface, in this case, because there's two variables. And our surface in question S is that graph. Okay. Recall a ways back, we talked about how whenever you have a graph, you can reinterpret it as being a level set. And notice that's the little quickie that I pulled here, right? So I just did a little algebraic sleight of hand. I hardly did anything here. I just moved this term to the other side. I subtracted a term. Hardly anything happened. And yet, now we are no longer visualizing S as being a graph. We are now visualizing this same surface S, same surface, now as being a level set. Right, you can see right here, we're looking at a level set because I have equals constant, level set of now this new function. And of course you do have to be careful, don't conflate these two functions. F, the thing whose graph is my surface, not the same as this thing, G, whose level set is my surface. Yeah? Everybody good? Okay. All right. So having reinterpreted this as being a level set, let's fooey on all this graph business. We don't need that anymore. I'm looking at a level set. I want to understand this tangent plane to a surface I'm now viewing as a level set. How do I find the equation of a plane? Well, I need to find the normal vector. I need to find a vector that is perpendicular to the tangent plane. Well, if it's perpendicular to the tangent plane, then it's perpendicular to the surface, which means it's perpendicular to a level set. How are we going to find a vector that's perpendicular to a level set? Well, boom, right? What we just established, gradients are perpendicular to level sets. So that's the beautiful little foot in the door. All I have to do to find a vector perpendicular to a level set is just take the gradient, and I emphasize the gradient of this function called G, whose level set is what we're interested in. Everybody with me? And now it's just, it's all downhill from here. We've got this thing z minus f of xy. We've got three partials to take, x, y, and z partials. Here they are. Once you have the normal vector goes here in the equation for the plane. Here's the equation for a plane. And you dot this out and multiply it out, collect terms, move things around, and what you end up with is this very familiar formula that y'all will all recall from when we were first talking about partial derivatives and linear approximations and stuff like that. Okay, so again, I just glossed over some details. I think it's readable. Give it a look. As always, office hours if you have any questions, if you get stuck on anything. Okay, the example I have here on the next page is, in retrospect, I think kind of a silly example. It does literally exactly what we did on the previous page. I start off by looking at a graph, and I just reinterpret it as being a level set in the usual way. I just take the right-hand side and subtract it over the left-hand side, and presto, I have a level set of now a new function, and this new function is the function whose gradient is my normal vector. And again, there's some arithmetic to be dealt with there, but that's the exact same idea as in the previous page. All right. Okay, so moving along. The implicit function theorem, this is a really wonderful topic that I would love to treat in such a way that it would take us a couple, 3 days to go through it rigorously and properly. And we don't have time for that. It wouldn't be Math219 appropriate either. The treatment that I have here is an attempt to give some sort of a intuitive sense for how the implicit function theorem works and why we care about it. I'm going to just hit highlights on that. This is something that I think it's important to understand why we have to care about the implicit function theorem, even though we're not really going to really give a full treatment of the implicit function theorem. So here's the main idea. I'm going to start with an equation involving two variables, which of course gives me a curve. Notice this curve is currently given as a level set, right? X and Y are both input variables to this function capital F. Y is not given as being a function of X. In fact, Y is not a function of X. You can see failure of the vertical line test in various places, right? Just catastrophic failure. Y is not a function of X. Okay. Now that said, though, I want to ask a different question, a more subtle question, and that is, can I view Y as being locally a function of X? And what we mean by locally is, if I were to restrict my attention to a little ball, a little disc, some small little region there, and only look at the curve, the part of the curve that is within that little region. So this is, I'm going to basically throw away most of the curve. I don't care about this anymore, and I don't care about that anymore. I want to look just nearby a given point. In this sense of locally, in other words, looking just at that part of the curve alone, now can I view Y as being a function of X? And notice that, the function passes the vertical line test, no problem. Right? So even though Y is not globally a function of X, if I restrict my attention, just to a little yellow ball here, right? Then locally, y is a function of x. Does everybody see what I'm talking about there? Yeah.
So what does it mean, like the vertical line test?
So the vertical line test is a way of thinking about the question of whether what you have a picture of is actually the graph of a function. Because functions, any given function can only have a single output value, right? And the vertical line test, let's look back at the original function that we were looking at. The fact that this vertical line hits here and here and here means that for this value of x, there are multiple different values of y that if this were a graph, each one of these three output values would have to be the output value for this value x. But a function can't have several output values, and so the punchline is if a vertical line hits a curve more than once, it can't be a graph. Does that make sense? Yeah. So that's all that is. All right. So so this is not a graph, but locally, again, if I just restrict my focus, small enough, and by the way, when you say locally, you get to decide how small that little yellow ball is. You can make it as small as you need to for your purposes. Right? So locally, in some appropriately myopic sense, near that point, the curve is a graph. Y can be viewed locally as a function of x. And the reason we would care about something like this is that, well, look, I might be interested, for example, in finding the slope of the tangent line. And notice, in order to talk about the slope of the tangent line, all I need to know is kind of what is the curve doing nearby. I really only need that local behavior to understand a tangent line. I could not care less what's going on up here if my question is just, but what's the slope of the tangent line? Okay. All right. Fine. So locally, here, yes, y is a function of x. Here, yes, y is a function of x. But wait a second. What about here? At that point, which, by the way, the point I'm pointing to here is the point that is where the curve is in the process of wrapping under itself. You might say where there's a vertical tangent line. That's the point that I'm talking about. And the way I have this curve drawn, I maintain that not even locally at this point is y a function of x. This is just this point here is there's something really wrong with this curve from the if you want to think about y as being a function of x, you're in pretty big trouble at this point because the curve, however little of it you look at, however locally you restrict your attention, you're going to fail the vertical line test. That's intrinsic to what the curve is doing there. Is everybody on board? Okay. So now, broadly speaking, why do we care about this? It sounds very sort of like mathematician-y, sort of like uptight, formalities. The reason we care is because we might want to talk about a derivative, right? We might want to talk about dy dx. And underappreciated point is that when you talk about a derivative, derivatives only are something that you can do to a function, right? So if y is a function, then you can talk about the derivative of y because y is a function of x, and that's what you do to functions of x. But if y is not a function, this becomes meaningless nonsense. There is no interpretation of dy dx if y is not a function of x. It's just nonsense. And if you're doing math, this is, to state it mildly, to be avoided, right? We try not to write down meaningless garbage, even if we possibly should happen to, discover later, whoopsie, it was, I see now in retrospect that was a problem, right? No, we try to just never write it down in the first place. So what we're going to worry about is how can we establish that y definitely is a function of x before I start writing down things that might have me guilty of writing down garbage. Does that make sense to everybody? All right. So the argument, and again, this is not at all intended to be rigorous. This is intended to be sort of intuitively satisfying. The idea is if you have a problem, let's see here. Let me get into highlighter mode. This is what a problem looks like. Right? The problem looks like that. The problem is if the curve is at that very moment in process of wrapping under itself. That's the problem. Okay, well, another way to say that is that it has a vertical tangent line. Oh, okay, now, but keep in mind, we're talking about a vertical tangent line to a level set. Again, this is a level set, and we know gradients are perpendicular to level sets, and so a vertical tangent line would mean that you have a horizontal gradient, and now let me remind you what the formula is for the gradient. The gradient is partial of f with respect to x, partial of f with respect to y. If that's horizontal, then that means that its second component would have to be 0. Horizontal. So, if you have a problem, this will be what you might call a symptom of that problem. Right? Unavoidably, if you have a problem, that y partial is 0. Is that cool? All right. All right, and now I'm going to take this argument that we've just made. If you have a problem, then the y partial will be 0, and I'm going to wave the magic wand called contrapositive. Right? Contrapositive means you turn it around and say not in front of both sides of the implication. And if that y partial is not 0, then you do not have a problem. And you're in good shape. Y is a function of x. Go ahead. It being as it is a function, take the derivative of it. Go for it. It's all fine. Not a problem at all. That make sense? Yeah.
So in the book, when they talk about the subject, they impose like a lot more restrictions.
Yeah, as a broad statement, the book is more rigorous than Math219 is supposed to be. So don't worry about anything that's more rigorous than what I'm giving you here is more rigorous than we need to be in this class. And it's not that it's not important. It is, right? It's just that that's not what Math219 is. And it's appropriate for a different course like 222 or 431 or something like that. Yeah.
Okay, so this is like the definition that we need to use.
This is all you need to worry about when it comes to implicit differentiate the implicit function theorem. Yeah. Okay. Now, what we've done here, you could argue, is cleaning up a mess that was left in single variable calculus, because in single variable calculus you do deal with curves in the xy plane, and you probably saw implicit differentiation in your Calc 1 or Calc 2 maybe. It depends on how your courses were structured. But you've probably seen that before, but they don't talk about gradients because it's single variable calculus. They can't. But arguably this is a multivariable take on a single variable question. Now, I'm going to give you a multivariable take on a multivariable question. So suppose that we have now an equation involving 3 variables, right? So this is definitely purely multivariable now. We got some function being a constant function of 3 variables, thus giving me a surface like I have drawn there. And I'm going to ask the same question. Can I view one of these variables, in this case z, I want to view z as being a function of x and y. And in most cases you can. Again, locally is all we really care about. In the vicinity right there, if you have some point in here, right, and you look in sort of that little neighborhood, well, no problem. Vertical line test, fine. Right? That at that point, locally, z is a function of x and y. All good. Likewise, various other points on this surface, and the problem happens when you look at a point like this. And the reasoning that explains why this is a problem is morally identical to what we just got through looking at. It's a problem because at that point, the surface is in the process of wrapping under itself, which is possible only because we have a vertical tangent plane, which means that the gradient of capital F would have to be horizontal, and a horizontal gradient would mean that the z partial is 0. And so again, we get this same sort of a connection. If you have a problem, the z partial has to be 0. Let's say that backwards and upside down. If the z partial is not 0, then you don't have a problem. Okay. Now, before we state the theorem, I do want to point out there's a nice sort of coincidence here, memory tool, you might say. And that is, notice when I was trying to view y as being a function, then it was the partial with respect to y that I had to look at. Notice, likewise, when it's z that I want to view as being a function, right, then it's the partial with respect to z that I need to look at. This pattern holds, and again, I'm just going to wave my hands at that. We don't need to, get all rigorous about it. The pattern holds whatever the dimension, whatever variable in the domain you want to reinterpret as being a function of the others. Whichever variable you want to view locally as a function, that's the variable with respect to which you take a partial and confirm that it's not 0. So that's what I had, the little summary that I have down here. Always take your partial with respect to the variable that you want to view as a function. Nice and simple and pithy. Okay, so example. Here we go. I want to, let's see here. Where's my button here? There we go. So here's an equation. Yikes. Cubic, multiply cubic, right? Bad. We don't like that. Question, is x locally a function of y and z near the given point 1, 2, 3? Can I view x as being a function of y and z? Well, don't try to determine that from the plot, right? I haven't got the slightest idea what this thing looks like. Right? Pretty ugly looking. But, again, following the rule, whichever variable you want to be a function, take the partial with respect to that variable. I want x to be a function. I take the partial with respect to x. What do we take a partial of? Well, we take the partial of the function whose level set we're looking at. Again, the thing that made all this work is that we were looking at a level set specifically of a function called f, and that's the thing whose partial we compute. Right? So this is what decides the question. The partial of the function whose level set I'm looking at with respect to the variable that I want to view as being a function itself. And so you just compute it out. Here's the general formula. Keep in mind I'm interested in what's happening near this specific point, so I compute at that specific point, which makes our partial become 4, which is not 0, and then per the implicit function theorem, not 0 means yes, all good. I can, at least locally, right? Only locally, but I can view x as being a function of y and z. Really not obvious from the algebra, right? But easily concluded from the implicit function theorem. Okay, and we are out of time, so we'll drop it right here. We'll pick up here on Wednesday. See y'all later. Have a good one.